So yes, we are really happy and fortunate to have Shafi and Dan joining the Fireside chat today. So, right, so the MOOC and the hackathon is about ZKP. And so there are a lot of really interesting topics to discuss. So maybe we can start something simple, since there are also newcomers, I think potentially in the audience as well. So maybe given Shafi and Dan's rich experience in the space, so maybe you can just first talk a little bit, what's your favorite analogy for explaining zero-knowledge proofs to someone who's never heard of them before?
Well, there are many analogies over the years, you know, because you're trying to explain zero knowledge, but it really depends on the level of the listener. So if it's a child or it's an adult or it's an expert in the field, you would give a different explanation. But I saw something recently, so I'm going to use that, which was by a son of a colleague of mine, where he saw a movie episode of this a series called Suits, where they're lawyers. And one lawyer, and the case is that they're accusing a firm for doing inside trading or something, and because it doesn't make any sense that they have such an incredible track record at earning money. And he's saying, no, we have software that manages to trade properly. And they say, well, expose this software. He says, if I expose the software, then I'm going to lose my edge. And zero-knowledge proof would enable you to prove that you have the software that produced these predictions without revealing the software. So that's kind of a nice example that came out of nowhere. They didn't actually use zero-knowledge proofs. They didn't know what the solution is. They just presented the problem. But I think it's a good way to explain.
Yeah. I guess the public isn't quite aware of what's possible and what's not possible. Right. So let's see. So actually, there are two aspects to zero-knowledge proofs, right? There's the zero-knowledge aspect, which is a privacy aspect, and then there's the other part we also care a lot about, which is the succinctness aspect, which is that the proofs are very short and easy to verify, at least in the context of snarks. And so Shafi gave a zero-knowledge example. I think you all know the Where's Baldo example for explaining the privacy of zero-knowledge. Where's Baldo, by the way, to give credit where credit is due, Where's Baldo is a paper that was written by Yael Naor et al. When she was about 10 years old. Yeah, so kind of a cool paper to check out. There is Sudoku examples, right? I have a puzzle, I have a solution to Sudoku, and I want to prove to you in zero knowledge that I know the Sudoku. So those are very simple examples. Since Shafi gave a zero knowledge example, I thought I'd give a succinctness example. Yeah, so how do you explain succinctness to the public? Well, at least to the more nerdy public, which is to say, I hope many of you have read The Hitchhiker's Guide to the Galaxy. Right? You remember in The Hitchhiker's Guide to the Galaxy, there's a computer there, it's called Deep Thought, that the people ask it, you know, what's the meaning of life, the universe and everything? And then it says, ooh, it's an interesting question, I have to think about that. And he says, it'll take me 7 million years to calculate the answer. So they let it run for 7 million years, and the answer is? 42, right. So with a succinct proof, actually Deep Thought could actually prove that it did the calculation correctly and that the answer really is 42. So the verifier doesn't have to run for 7 million years. The verifier can just look at this very short proof and be completely convinced that the answer to life, the universe, and everything really is 42. So easy explanation. By the way, I do have to say that just this morning I gave this explanation to some reporter that I was talking to, and he says, that sounds impossible. How can you possibly verify computation that takes 7 million years? How can you possibly verify it in like 5 milliseconds? It sounds impossible. Can you give an example of how, like a real-world example where you can easily explain how succinctness works? Why is it possible? And honestly, this is a challenge for all of you. If you guys can think, Shafi, maybe you have an example, but if you can give like a very simple example of why is succinctness possible, I'd be thrilled, because it's not easy to give such an example.
I think when you talk about solutions to a puzzle, right? The puzzle may have taken a long time to solve, but verifying the solution is very easy.
For an NP statement.
But this guy knows about NP.
Yeah, okay. Yeah, perhaps. Anyhow, I thought this was like a nice, easy way to explain succinctness.
Great. Thanks a lot. So what was the most interesting or unexpected application of zero-knowledge proofs that you've come across?
How long do you have? Shafi, why don't you start?
Again, this is depending on your level, right? So I think the thing that was most surprising is that I heard that this thing about the nuclear disarmament, right? So this was quite a few years back. I think Boaz Barak was in Princeton then, and there were some physicists in a cafeteria talking about how they can do, let's say the Americans and the Russians at the time, they had nuclear warheads, and they want to convince each other that they're actually disarming nuclear warheads and not just some demi thing that looks like it. So they said, oh, maybe you could use a zero-knowledge protocol to prove that what you have inside of this warhead actually has nuclear capabilities. And they, of course, this is not digital information, but it's some sort of something about the technology of being a nuclear warhead rather than just looking like one. But they came up with a protocol that was actually quite similar in spirit to what we do in zero knowledge. It had something to do with how many electrons were being emitted, and it was sort of accounting and comparing to something that you knew was a nuclear warhead to things that you weren't sure of and you're trying to prove they were. So that was a surprising use. People were writing grants about nuclear warheads in nuclear engineering and zero knowledge, and that surprised me. But frankly, the big surprise for me was really in 1987, when after we sort of invented the idea of zero knowledge and showed a few examples of it, is that a paper came around that showed that everything in NP can be done in zero knowledge under, a one-way function assumption. And that was like going from a concept and an example to a very general result. It relaxed a little bit the type of zero knowledge, but that was kind of shocking. And from there on, there was a lot of possibilities.
Yeah, there are so many surprising applications. It's even really kind of hard to choose. I guess there are applications to building signatures with all sorts of properties like blind signatures, homomorphic signatures. It's really kind of cool that recently there's a lot of applications in learning for zero knowledge, right? You want to prove that you actually evaluated a model correctly without revealing anything about the model. So all those I think are really interesting. I guess we did some work on zero knowledge to fight disinformation, which I actually talked about at Berkeley before, so I won't say any more about that. If you're interested in seeing how that works, check out the Real World Crypto talk on that. And even using zero knowledge to actually prove that a program works correctly. So I can prove to you that a program satisfies its spec without ever giving you the source code, which is really kind of amazing, right? I literally just give you the binary along with a proof that the source code satisfies some public spec, and you won't learn anything about the source code other than what's revealed by the program itself. So there's really endless kind of very surprising applications.
Yes, yeah, great, thank you. And again, in the ZKP MOOC, we do actually cover a broad range of different applications. So I do encourage everyone to go check it out as well. So in the MOOC, we covered a lot of different topics. So what is the one thing that you wish more people knew or understood about zero knowledge proofs?
Okay. You go for it.
I go first, okay. To me, one thing that I think it would be nice is if, I believe the kind of words matter and terminology matters a lot. And we see the words ZK being thrown out a lot, even in applications that don't require ZK. So a good example is like a ZK rollup. Well, most ZK rollups actually rely on succinctness, not so much on ZK. So if I had a magic wand and I could wave it, I would maybe encourage all of you also, when you name projects, maybe if you're not using ZK, just using succinctness, maybe call it proof-based system or succinct system. And systems that do use ZK actually use privacy, zero knowledge for privacy, could actually use the terminology. It's kind of funny that ZK rollups use ZK, but a system like Tornado, which actually uses zero knowledge, doesn't have the words ZK in it. So yeah.
So I would say that you asked what I would wish got more attention. So I think everything has its time. So right now people are interested in blockchains, interested in succinctness, and willing to assume as much as you can, right, to get a very compact and a fast to verify proof. But there are things that you can do even unconditionally. So we're making a lot of assumptions, right, to get both soundness and zero knowledge and succinctness and so forth. If you sort of wanted to kind of step back and say, some of these properties you can get without making any assumptions whatsoever, whereas some of the you cannot make no assumptions and get everything. That is both the provability and the zero knowledge and succinctness. But you could get unconditional, let's say zero knowledge and not unconditional soundness. I think it would be interesting going forward to see different physical models of doing zero knowledge that would make it unconditional. So if you know a bit sort of, let's say about quantum, which I think you're going to be asking about next, maybe not. So there are some things like key exchanges that we can do unconditionally, in quantum, where we don't have to assume hardness of things. And I think that there is some of that to be uncovered also for zero knowledge once we allow ourselves sort of different models going from the kind of paradigm that we're in.
Or maybe one day we'll actually prove that some problem is hard, and then these constructions will become.
That's going to take more time.
That's going to take more time for sure.
Great, thank you. So earlier we talked about some surprising applications. So now, in terms of from the actual technologies or techniques, as an expert in the field, what were the breakthrough results that really surprised you?
Breakthrough results. Actually, Shafi, why don't you start with that?
So I guess I mentioned the original one that talked about the generality of zero knowledge. I guess another thing is that stuff that's less known, and it's not necessarily just zero knowledge. As Dan emphasized, there's something about the succinctness or the fact that you can prove a lot of things with very little memory, even without the zero knowledge property. So to me, the development in this field that was very surprising was that after starting with this first model, where there's a prover and a verifier, and you can talk about interaction or non-interactive, like snarks and so forth, there was this other models where you have these two provers, where and then you can get unconditional zero knowledge. And that morphed into something called a probabilistically checkable proofs, where there's sort of a long proof, but you only have to check a few locations, and still, if there is a mistake anywhere, you'll find the mistake with high probability. And that was sort of a revolution in complexity theory, and showed a lot of hardness approximation of a lot of problems. So again, it's more of a complexity theory development, but it was very shocking that it came from this zero knowledge proofs that had to do just with trying to hide something while you're convincing someone of a fact. And it turned out that way, where we are allowing probability of error, made that we could have much more efficient proofs than we ever thought, and locally checkable, because we allowed the probability of error. And that in itself kind of redescribed complexity theory. So it came from a very unexpected goal.
So you're referring to the PCP theorem. Yeah, actually, I guess it's kind of useful to say that all the snarks that we kind of know and love today, in some sense, they're children and grandchildren of the PCP theorem.
That's right.
Yeah. Actually, maybe I'll say one more thing about that, because I think that's kind of interesting for folks to think about. So if you had to summarize like the one algebraic fact that makes the PCP theorem and snarks work, at least one proof of the PCP theorem, it's kind of remarkable that everything follows really just from a very, very simple algebraic fact. Yeah, that a polynomial of degree n has only n roots. Yeah, it's really kind of that kind of elementary school algebra. Well, I don't know if elementary. That simple algebraic fact is literally what makes the snarks that we use today work, and actually goes back to the PCP theorem. What's interesting is that is only the original proof of the PCP theorem, right? Using algebra and polynomials and such. In fact, there's another proof of the PCP theorem, which doesn't use algebra, which is more combinatorial. And it's very interesting, actually, so the algebraic proof of the PCP theorem gave rise to all the snarks that we use today. Yeah, the combinatorial proof of the PCP theorem, maybe that's like an area that's just waiting to be harvested, right? Maybe there's a whole new direction to snarks that could be constructed just from that proof. So if there are any of you out there that are interested in kind of exploring a whole new direction for building snarks, maybe it's worth learning more about these combinatorial proofs of the PCP theorem. Maybe there's a lot more to harvest over there.
Maybe, but to me also, I think this is like the victory of algebra, which always is victorious in terms of this such beauty and richness, and it actually can lead to these amazing things. So
algebra. Everybody should just by the way, this is I think this is by the way a very relevant discussion. Let's zoom out just a little bit. I don't know if you are aware of this, but in California and in the rest of the country, there's a big discussion of whether algebra should be taught in high school. Yes, very big in high school. Very big discussions on that. And the fact that if you don't learn algebra, you will not be able to invent snarks, I don't know. I would say maybe that's an argument, well, not clear that's going to fly, but that's an argument that we could use, that in fact more mathematics is definitely needed in high school. But coming back for just one second, the thing that surprised me. So I guess just to give a little bit of the history in that, again, the original origins of snarks date back to the PCP theorem and the zero knowledge proofs. Amazing, amazing work. It's interesting that in the early days, much of the work that the prover was doing was polynomial time, but it wasn't quite linear time. Yeah, and in some sense, that looked like where we are. And one thing that was surprising and somewhat unexpected and actually enabled a lot of what we do today is the fact that in the early 2010s or so, all of a sudden there was a sequence of provers that emerged that were actually linear time or quasi-linear time, and that really is what makes it possible to do what all this group is actually doing today. So I just wanted to highlight that because that is kind of an amazing jump that happened about a decade ago.
Great. Yeah, thank you. So in the past decades, we have seen the efficiency of proof systems, related to what Dan just mentioned, proof systems have improved by orders of magnitude. Again, that's why there's a big motivation for the ZKP MOOC and also all this hackathon and so on. And also, I think many of you have heard about the recent ZK launches and so on. So the question is, where do we go from here? Where do you think we still have, orders of magnitude efficiency improvements that down the road, and where do you think these improvements will come from?
So I will take. I actually was going to say that you should say it, but we've just been spending a week in a workshop at Simon's, where a big topic is verification, and it's surprising. There's a lot of new things that are coming up. For example, like batch verification, which is also done in snarks and stuff like that, but in very clever ways of doing this. So sort of like you can do on bulk lots of verification with essentially proportional to one witness length, and I could see that those ideas of batch can be not just for size, but for other things as well. That's, to me, as a more theory-oriented person, is where I would look.
I have to say, I remember this quote from Don Knuth that said that he wishes people would stop writing papers on sorting so he can sort all the work on sorting. Because he was having trouble keeping track of all the work on sorting. This our field, these ZK proofs, both the theoretical directions, the more practical directions. It's incredible to see what's happening. The community has just grown by so much. Look at how many of you are in the room. 20 years ago, if you had told me that we're going to be building a ZK EVMs, I would have thought, my God, this is like science fiction. Yeah, how many? Just think about that. How many examples do we have where 20 years ago we would think that something is science fiction, and 20 years later, not only is it doable, it's actually in production and people use it. How many examples like that do we have? Not that many, right? Oh, maybe landing rockets. What? ChatGPT. Okay, fine. Well, yeah. So, fine. You got it. Another ChatGPT. Another example. We got 2 examples. Yeah, not that many, as I said. So, but you're asking where will the next improvement come from? I think there's a lot of avenues to explore. Of course, there's all the wonderful theoretical avenues that Shafi mentioned. I would say that also recursion and folding schemes have gotten a lot of attention recently. Folding schemes in particular. I guess you guys, some of you already asked me about Nova and Supernova and Hypernova. Those are really interesting directions for folding schemes. So probably there's a lot more to do there, and I would guess that that's kind of where a lot of the next improvements will come from.
Yeah, thank you. Okay, so follow on that question. So another dimension is we've seen advancement of quantum computing. And hence, it's really important for us to work on post-quantum secure zero-knowledge proof approaches. And so the current solutions, they still have large proof size and so on. There's still a lot of room for improvement. So which line of research do you think are most promising to resolve these issues?
Post-quantum.
Yes.
Shafi, do you want to go first? Or?
Sure. So again, for one thing, I think you're thinking about a particular set of proofs when you talk about things that are not post-quantum. But there are, you can do these things also based on lattice-based assumptions, which do seem to be, and hashing functions. And furthermore, I want to emphasize something I said before, that some of the schemes, which are have unconditional zero knowledge and computational soundness, which says that you will have everlasting secrecy even when quantum computers are around because it's unconditional. So if you have aspects of this that are proved unconditionally, and those are the aspects you care about, then those things actually are not going to be broken if quantum computers are going to be built. But also, I wouldn't be so worried in the near future.
So Shafi said exactly what I was going to say. That's excellent. Right. So when it comes to quantum computing, I guess we have to separate between data integrity and data confidentiality, right? So for confidentiality, things that we encrypt today, we can worry about quantum computers 30, 40, 50 years in the future. You know, all of us actually have to write a lot of recommendation letters, and we have to send the recommendation letters over by email, and they're all encrypted. If somebody's recording all those ciphertexts, you know, even in 30, 40, 50 years from now, if they're decrypted, you know, maybe there'll be some interesting, you know, social aspects to that. I only write good letters, though, so for me, it's not a problem. So that's an example where confidentiality is something that we might need to worry about in the near future. Integrity is something that we can worry about more as we get closer to the world of quantum computers. There we just shift to a system that's quantum resistant. And we have actually snarks that are quantum resistant. Starks are an example, right? Hash-based Starks, quite practical. There's a lot of theory work that's quantum resistant. So in some sense, it's always, I have to say, it's a little surprising to me that we get this quantum question as much as we get, right? It's good that the public is worried and interested in quantum computer, but from a cryptography point of view, more or less, we know what to do, right? We know what to do. And so it's like we don't have to freak out if there's like a quantum computer that's going to come out soon. We know what to do, although, as I think we agree, it's still very, very far in the future.
Absolutely.
Great, thank you. So earlier the audience already mentioned ChatGPT. So that's, of course, one direction, one area that has seen huge excitement. And the advancement of ZKP technologies is another really exciting area. So in the area of AI, I think people have heard a lot about the discussion, the ethical questions, and right, these type of questions, to the extent that like over 1,000, I think now it's maybe even 10,000, right? Like researchers, scholars have signed a letter to say that, to actually even call for the pause of AI research, these large language models, in general, this area for 6 months to figure out how to have a better way, to figure out a better way how the society together can progress in a responsible way. So one question is, what do you think about in the area of zero-knowledge proofs? Do you think there are ethical concerns, implications as well? Right, yeah, that's the question.
I see. Do you want to take that, or do you?
Okay. It's a surprising question because I think that actually zero knowledge is only adding to the ethics rather than the other way around. Because what are we saying really fundamentally is that you don't have to store secrets, and you can still convince someone that you have it, and they can verify it without actually having access to your information. That's even if you look at the most basic example of verifying passwords without actually knowing what your password is. So in a sense, it seems to me that we are only making the privacy stronger, the burden of people to keep information which they're not good at, goes away. We are verifying, you could verify the legal contracts, there's somebody's access to information without knowing details about them. So the question surprises me. I, of course, hesitant to say that there are no ethical problems, because maybe there's always some ethical problems I haven't thought about. Perhaps there's less accountability. So you would say that down the line, maybe it wasn't a good thing that you let someone prove with high probability that there, maybe without giving you the evidence, because there is some merit to having some way to account for it. If there are no random coins in the world, like we're assuming that there are, randomness is out there. Maybe it's not true. Maybe everything is deterministic. Maybe we are making people think that something is true and it's not the case, and therefore there's some potential for misuse. I can't think of anything else.
Well, so privacy that's enabled by ZK, I think there are ethical aspects to it. Okay. And so,
learned something from this.
great.
Fire chat.
Great, yeah. Maybe just to give one example, something that often is brought up by law enforcement, right? So imagine, so as we know, ZK proofs.
Accountability. Yeah.
Well, ZK proofs are used to provide privacy, complete privacy in the payment system, right? There are many blockchains that use ZK proofs to enable anonymous payments, private payments. Well, as you know, there are folks in law enforcement that have problems with completely private payments where there's nothing we can do. And I guess we've seen an example. Tornado Cash was an example that was actually shut down because it was fully private, and therefore it was actually abused, and therefore was not allowed to operate. I think the answer to us is, we live in the real world, right? I mean, there are laws that we have to comply with. It's not always clear when you talk about the global internet. It's not always clear which jurisdictions' laws you need to comply with. But let's say we are focused on the U.S. There are obviously we have to comply with U.S. laws. And so I think when you mention ethics, I think the question is, the challenge to technologists is, how do we design systems that provide the best level of privacy while complying with the laws of the U.S., which is, it's the fact. We have to comply with the laws of the U.S. And so that actually is, it actually makes the technical problem technically more difficult, more challenging, more difficult. And so, yeah, we actually don't know what the solution is. We don't know where things are going to go. And this is a pretty interesting time. It's kind of an area where there needs to be a lot of conversation between cryptographers and lawyers. We've actually written a paper with lawyers on, what does it mean to do. I mean, how do we reconcile this issue for a need for privacy in some systems with a need to comply with laws? So yeah, I think it's a pretty interesting topic.
So I get you. I would say that a difference between this and ChatGPT, there's difference because these are different things and there are different ethical questions, but the difference is that I think that zero knowledge was founded and continues to be grounded in the sentence, in math we trust. We actually prove the things that we can define clearly what it is that we are guaranteeing. Okay, we're saying this is what we guarantee. We can prove it maybe under some assumptions, but it's very explicit. Right now, to me, the issue with these large language models and so forth is that we don't. They're not very clear about what they provide and what they don't provide. Where are the limits? Because it's so beautiful, it's so amazing. You can do more and more and more. So there's not clear how it generalizes, not clear if it's robust, not clear exactly what you're guaranteeing, and that's where I think there's a lot of worry. Where is this going? If it was very clear what you're providing, what you're not providing, maybe then you could curtail it. That is actually because the nature of our field and where it comes from, it is very much grounded in clear definitions and fairly clear what we provide. And I think there's a difference there. So we can discuss the ethics of but at least we know what we're providing, what we're not providing.
I have a question that's okay to ask. You mentioned that ChatGPT-like models, they don't know how they're getting what they're getting, and people are not so sure what they're getting. So can this be an application for GK where
Sure.
we bring
Sure.
accountability?
Sure. For trustworthiness, yeah. I think that there's lots of...
The question is whether ZK can help ChatGPT provide more robustness and guarantees of the results.
Yeah, I think that's a great field, and obviously people are working on it. I think all these methods of verification and trying to figure out consistency and things of that sort, which is in the nature of what we do, are extremely applicable. Of course, the problem again is you can't really formalize what they're doing. If you could formalize what they're doing, you could use our methods to show whether they achieve it or don't achieve it. So still, the key challenge is to formalize what is it that is being done there, and it's a fascinating question.
So first of all, this conversation proves a theorem that every technology conversation these days within 20 minutes converges to ChatGPT.
It's very exciting.
It is very exciting. I agree. And also just to recognize the limits of what crypto can do. I ask ChatGPT simple questions, and it very confidently gives me wrong answers. Right? It's not clear that us cryptographers can actually help with that. That's more of a question for people who are who are training the models. But to Shafi's point, actually, the crypto field we're in is a very, very precise field. Yeah, it's very important to remember all the statements we make, everything is very, very, very precise. It's kind of a very mathematical field in that sense. Everything that we guarantee comes with a very strong degree of precision, so you can tell exactly what's guaranteed and what's not guaranteed. And I think the challenge is then to policymakers, in some sense. The message that we always give is, you tell us what the policy should be. We can come up with efficient zero-knowledge proofs to implement that policy. What should the policy be? And then we get blank stares from the other side, right? And so the challenge is actually, what is the policy?
But there is discourse between. There are discussions between policymakers. Let's say in GDPR, there was all these examples where they say roughly what they want. They want it to be you can sort of delete your information. You want people not to be singled out and so forth. So it is partially on us to define that in precise terms and say, if you define it like this, we can provide it.
Mm-hmm. I think the bottom line, I think, is that there's room for a lot more dialogue between our community and the policy making community. And so, please be open to that, right? So this is a message to all of you. Please be open to that. I think it makes a lot of sense to talk to the folks in DC first to explain what zero knowledge can do. It's because it's a magical thing, right? If I just told you off the bat that this is, how can this be done? You would think that this is impossible. So first, explain what the technology can do, and second of all, work together on what is it that we should actually, what policies should we be enforcing.
Great.
A quick follow-up: is a zero-knowledge proof deterministic or is it probabilistic? So we can say for sure that
There's a probability associated.
Yeah. The question is it okay? Yeah. The question is does it give absolute guarantees, or does it give probabilistic guarantees? And
so everything here is with high probability, but it's so high when we say like 1 in the lifetime of the universe. So let's put it this way: the chance that you will find a mistake is maybe you could when the universe ceases to exist. So that's sort of good enough.
Yeah, the probability of error is so low that it's the same as you just randomly guessing a cryptographic key. Like, you're so lucky that you ended up just guessing a random key, and that happens to be like a decryption key. So that's so unlikely that we say it will never happen. We have questions in the back.
That would be probabilistic.
Yes.
But probabilistic with such a low error.
It's a non-zero error.
But such a low error probability that you might as well.
No, that's okay. It's probabilistic.
So maybe we'll just have another 1 or 2 questions, and then we'll open up to the floor just for a few questions, right? Okay, so we have a lot of newcomers in the ZKP MOOC and in the field and so on. So what would be your advice to someone just starting out in this area?
First of all, take the ZK MOOC. That's step number 1. Take the ZK MOOC. I have to say, this area is it's really I'm thrilled to see that there are people who are coming in who are not trained cryptographically, and they're able to pick up the topic and kind of self-study and learn by themselves and come to the forefront of the space. So it's really wonderful to see that. So I think the main message is, don't be afraid. Yeah, I mean, nothing is too complicated for you to understand. It's all understandable. There are very good tutorials out there in the ZK MOOC in particular. If you have questions and you want to join like a group that studies this topic as a whole, there's a ZK Study Club. Just Google that, the ZK Study Club. That's a wonderful resource to join. It's kind of a group of people from all over the world. It's open to answering questions and another way to come up to speed. And then there are actually textbooks that are appearing on the subject. So Justin Taylor has a very good textbook. You can take a look at that. And so there are more resources that are coming up. But of course, start with the ZK MOOC.
It's just a generic question. When somebody asks me, what advice would you give? I think it's like precision medicine, Depends on what your ailment is, or what your taste is. So if I have had many students over my career, and you cannot really have the same advice to 2 different students. You have to find out what they what their strong talent is, what they're interested in, and then maybe if you have the right intuition as an advisor or as a teacher, you could tell what is it that's what they're gonna do well, what is gonna spark their interest. It's too generic a question. It's like, you've all seen The Graduate probably, where he says what you should do and you should go into plastics. It's kind of a joke, right?
Great. Okay. One last question, then we'll open up to the floor for a little bit. What is the biggest challenge in the space that's at the moment, according to you, and what would you want to see happen in the space in the next 10 years?
Okay. I'm going to take that and zoom out a little bit. I'm going to interpret that as a question about cryptography in general. Where is cryptography going? What's the biggest challenge? This is an amazing time to be a cryptographer. We were just talking about this before the panel. I don't remember, I've been doing this a long time. I have to tell you, the last 5 years have been amazing. This is an amazing, amazing time to be a cryptographer. There's so many interesting problems to work on. There's so much interest. There's so many new ideas. The community is growing. So many papers being written. But still, there's a lot of work that needs to be done in cryptography. And maybe I'll give 3 examples. Literally. I'll start with fully homomorphic encryption. Yeah, if we had a fully homomorphic encryption system that was, say, 5 times slower, only 5 times slower than computing on plain text, it would change the world. There are so many industries that are literally waiting for fast, efficient, fully homomorphic encryption. It would just enable us to do things that we can't even dream of today. You might say, oh my God, that's never going to happen. But that's just not true. Yeah, fast, fully homomorphic encryption, 5 times slower than computing on plain text. It literally could be one idea away, right? We have fully homomorphic encryption. Right now, it's a lot slower than computing on plain text. Maybe one idea will enable us to speed it up, and then we'll be there. So it's a wonderful, wonderful area to work on. And there are lots of problems like that. I'll give another example. There's again, an incredible tool that's been developed in crypto in the last 2 decades. It's called obfuscation. Maybe many of you have heard of it, indistinguishability obfuscation in particular. Today, it's extremely inefficient, but there are, again, industries that are waiting for indistinguishability obfuscation. And just to give you one example, it would allow us to store secrets on the blockchain, which today we cannot do, right? The blockchain today cannot keep secrets. With secret keys in particular. With obfuscation, we could do it. So literally, there's a whole industry waiting for us to come with efficient indistinguishability obfuscation. And again, it's one of these things where you say, oh my God, that's never going to happen. Well, no, that's not true. We might be just one idea away from coming up with an efficient construction. So it's like everywhere you look. And I could keep on rattling these problems, right? Witness encryption, an incredible tool. Again, extremely useful on the blockchain. We can't use it today because we don't have efficient instantiations. Again, one idea maybe would get us to efficient witness encryption. So our field is just littered with all these problems that we would love. The industry is waiting for us to come up with solutions for, where we're just, in some sense, we are not delivering, right? The industry is waiting, and we're not coming up with good enough solutions. But maybe it's all just one idea away, and maybe one of you will have that idea. So I foresee a really rosy future for cryptography. I think this area never gets boring. Yeah, it looks like sometimes, oh my God, many of the problems have been solved, and all of a sudden there are a whole new category of problems. This area never, ever, ever gets boring. So I'm really happy to see so many of you here, and I really encourage you to keep studying more and more cryptography, because it's one of those rabbit holes that goes to infinite depth.
Yeah, great answer. I think there's a difference between obfuscation and fully homomorphic encryption in the sense of how much time it will get there to level of efficiency. Because with FHE, it was pretty amazing what it was like in 2008 versus what it's like today. So it's not 5 times without being encrypted, but it's way better than it was. And for certain tasks, it's even fast enough. Obfuscation is still, I think, several ideas away rather than one. But as you mentioned, there's these amazing gadgets that people have defined in crypto and have shown that in principle they're doable, like witness encryption or something called functional encryption, that if you have separate keys go to separate people, and if you have a key, then you can compute certain function of the underlying message, but not others. There's a lot of stratification of things that you can do. And it is true that the difference between defining them and actually using them is in some breakthrough that's going to make this efficient. And in general, I do think that the combination between machine learning and cryptography has a huge future to it. Doing all these operations on encrypted data, when selectively encrypted, maybe some stuff is encrypted, sometimes isn't, being able to combine very, very large data sets to be able to make much more progress about things which are important to us, understanding, medicine, and so forth. I think there is a barrier there, the privacy barrier, that doesn't let us use the kind of ML tools that we could to the extent that would be wonderful to do. And if we could combine those two things together, there's really a lot more than we can do.
Thanks. So now we do want to get back to our demo and award, but we want to just take a few minutes to maybe, right, so I think there were a few hands from, right, please. Mm-hmm.
So you mentioned unconditional zero knowledge. Does that eliminate the soundness error, or is that eliminating one-way function assumption, or what is that?
So the unconditional the result that what I was. So the question was, that I mentioned that there's something called unconditional zero knowledge, and the question was, is that about the privacy or about the soundness? I think that's what your question is. And what I was thinking, you could go either way, but the one I was referring to is where the soundness depends on a computational assumption, but the zero knowledge does not depend on a computational assumption. And the reason I mentioned it in the context of quantum, so if you want something, you want to check something now with respect to the ability of breaking soundness, you can't do it right now, but maybe later you'll be able to break that assumption, but the zero knowledge is going to be maintained because it's unconditional. So we can't do both. So we're giving up somewhere, either in the zero knowledge or in the soundness, or we are throwing into the mix some sort of a physical assumption, like the provers are separate from each other, or there's a speed of light, or something like that, so they can't talk to each other.
Hardness and correlation and tractability and one-way functions, and then there's a super practical set of how you can plug in ZK in interesting ways, like bridges or the EVM, and then there's the middle ground of making new polynomial commitment schemes. I'm really curious, obviously we can't focus on all of them, even though different people are focusing on all of them. Is there any place on that spectrum that you all think right now is the time to really hone in on, and you find that you'll get the most utility out of focusing on right now?
There's no unique answer to this. It really depends. I think it really depends on what precision medicine. Yeah, it really depends on what your interests are. I would say if you're if you're interested, for example, in minimizing assumptions, right? Then there's a huge community on the theory side working on how to build proof systems with the least possible assumptions. Beautiful, beautiful ideas coming up there. So that would be one direction. If you're a systems person, you're interested in designing programming languages that are especially well suited for snarks. It's kind of remarkable that when you see the work that's being done on the snark frameworks, it has a lot of hardware design flavor, right? Because a lot of them are basically designing in some sense, virtual machines that run on this snark hardware. And the snark hardware is not like anything the VLSI people build. Yeah, it's very different hardware. Things that are expensive on one side is cheap on the other side, and vice versa. So all of a sudden, there's a lot of design work in how do you actually design the most efficient virtual machine that's appropriate for the snark hardware. So if you like that kind of work, there's a tremendous amount of progress happening there. And even in the middle ground, like you mentioned, designing snark systems, designing, I call this above the hood and under the hood. Yeah, above the hood is basically just using snarks as a black box, and under the hood is kind of opening the black box and designing better snarks. There's also tremendous progress happening in that area as well. So it really, this is why this area is so amazing. It's there's everyone can contribute. Right? If you're a systems person, you go one side. If you love math, you go to the middle. If you like more of the complexity theoretical stuff, theoretical type of work, you go to the minimizing assumptions. So there's amazing stuff for everyone to contribute. So I wish I had a precise answer for you, but that's the best answer I can give.
Okay, one more question. Since we don't have.
I think kind of somewhat similar question, but also I'll phrase it maybe a bit differently, which is, what do you think is kind of the biggest sort of bottlenecks to the adoption of the technology? Do you think that's more
Oh, sure. So the question is, what are the bottlenecks to more to greater adoption? Honestly, the fact that today, if you're a company that's trying to deploy snarks, you need to hire cryptographers. Yeah, that's not where we want to be, right? Where we want to get to is if you're a company or a project that's trying to use snarks, you should be able to use off-the-shelf tools and not shoot yourself in the foot. I think that's the end goal. That's the end vision. Now, we are making progress towards going there. Yeah, there are companies that make it possible to now take just regular C code, compile it, run it through their compiler, and poof, you have a snark system that proves that the code ran correctly. So that starts to minimize the requirements on developers that developers need to know in order to use this technology. We're not there yet. Yeah, these tools are still in their infancy. They're still not that easy to use. You still need to be a cryptographer, honestly, to use them correctly. And so this is sort of an engineering effort, but it's a very important engineering effort, right? Making it as accessible and as easy for developers to use the technology is kind of what's going to unlock basically universal adoption of the technology.
So I'll answer your question in a different way because I'm not sure whether that's what you were looking for. But so I could take your question differently. Say what is the bottleneck? Why isn't everybody doing like this fancy crypto? Why isn't everybody doing zero knowledge? Why isn't it the case that companies who are doing really FHE or MPC or zero knowledge are not it's not the next Apple or Google yet, right? And the reason I think is because there isn't yet, we haven't convinced people, or maybe we haven't found it ourselves, to be completely honest, of an application that cannot, a use case that cannot be done differently. A use case where it's very clear that if you do this, you can, let's say, maybe hit a market that you wouldn't be able to do otherwise. And that's why I gave the example of an AI type of application where there's a lot of documents, there's a lot of data you're just not going to have access to unless you use crypto. But by having access to it, you could get so much more utility. So that might be something where you just can't do it because you're not going to have the access, so you're not going to be able to get the utility. But I would think that that's what's convincing that you really are going to go elsewhere with the crypto rather than just protecting yourself or being more efficient is, in my mind, what we haven't gotten yet. But I don't know, but we're almost there. So my co-patriots here are much more practical and optimistic.
Indeed.
No, we will get there.
Yeah.
But I think that that's what's missing.
Okay. Great. So I know we have lots more questions, but we do want to get back to our the finalist demos and awards sessions. So thanks a lot. Thanks again, Shafi and Dan, for the really wonderful discussion.